just to make a safe behavior of your machine, your thing, your house, whatever. And the idea here is, you see we have put here the workflow, so we can on the one side have software components and model their behavior. So in this domain-specific language, it's called IEC 61499. Then you can model applications by connecting this components, we call them function blocks. And for the function blocks, currently we need to generate C++ code, which is then connected to our runtime environment, and you can compile it for different platforms. So here you have the BeagleBone Black, as we are using it here, but this could be a tremendous amount of different devices. So we have, I don't know, 6 or 7 different operating systems. And the advantage of using this is, as you're going to your things, you will find lots of different processors, lots of different operating systems, as we have heard, lots of different communication protocols, and we abstract them away for you so that you can develop your application and once and run your components on all these devices without any changes. And one thing what we also add is that once you have configured your application, you can even go online and see what's going on there. So like you can connect to your device, connect to your thing, and look there and see, you see here with the orange boxes, we will have a live demo afterwards, to hopefully if we have a connection here, to see what's going on and also interact with it. So like debugging on your device. So yeah. I'm out of time.
No problem. Yeah, same thing for other domains, eTries. It's a development tool based on the modeling language Room, real-time object-oriented modeling. We do have code generators for C, C++, and Java. Okay, C++ is a prototype, but the others are production level. We do a lot of rapid prototyping in application and rapid application development for embedded systems. It looks similar. We model structure and behavior of your embedded system. We generate the code. We add the runtime library for portability, so we can run on virtually any target with any operating system or even without operating systems. So big, small systems. We compile and deploy to the target, BeagleBone Black or others. So just to mention that, that's for all 3 of us the usual environment. Yeah? This or really small ones or really big ones, but not the BeagleBone Black. We use that one for prototyping or something like that, or for showcases like here. And then in the end, you can debug on model level, for example, by using message sequence charts to have a look at what your application actually did. And yeah, those 2 projects you can use to create those things, and the Eclipse SCADA you can use to monitor them. So next step is about our demo, and Jens is going to show you that.
So this is now specifically what we have here on this table. So what we have is we have a server component from the Eclipse SCADA. We have a SCADA client, which we just have a look at in a few seconds. And then we have BeagleBone Blacks in 2 different variants, because we have BeagleBone Blacks with eTries and with 4DAC. What we have on the BeagleBone Black is a cape. Now, yesterday, several people asked me, what's a cape? A cape is a shield. Now, what's a shield? A shield is something you put on the BeagleBone, like a Raspberry Pi. I think it's called Shield. For the Arduino, also it's called, I think, Shield. So this is just some hardware you attach to your BeagleBone, which then has some functionality. And we have a special traffic light shield or cape, which has 2 traffic lights on it, a button, so if you sit next to one, you can have a look. So that's the basic idea, and in the middle we have the cloud, we have some connectivity which might work or might not work, and this is also one thing we want to show here, how important it is to recognize the fact that this might be just broken. So this is, when we have a look at the software, what it looks like. Again, we have the 2 BeagleBone Blacks down here with the eTries runtime, which is using GPIO to communicate with the cape, with the board. And on the other side, we have the protocol which we use, which is SFP. That's a protocol we use here from Eclipse SCADA. So we have a C variant and a Java variant, so both sides can communicate with that. On the other side, we have 4DAC. here. So there's a slight difference from these two tools. For eTrice, you have one composite application which contains all the logic, and the libraries, and the actual custom logic that you have. For Fortiac, it's a little bit different. You have a more generic runtime with some basic components compiled in, and then you deploy your application inside that runtime. But I don't want to go deeper into that because we have two people who can talk more about that than I can. So I will have a look more here on the server side and the client side. So the server, of course, takes in the data from these devices. Of course, we have multiple BeagleBone blacks here, so the data is first aggregated just to reduce the number of values we have. We have 10 BeagleBones here. We have 5 Austrian, 5 German ones, so traffic lights behave different in different countries. But we try to aggregate the common state of these. Are they working? Are they not working? Is there any fault? Just to say, okay, we have all Germans, all Austrian aggregated. And based on this, we have monitoring and control. We will have a look at this in the demo. And then we have the client. So the client is the visualization tool, communicating with the server using the NGP protocol, which is also something which is coming from Eclipse SCADA, which is just the best protocol for us to communicate internally, to provide all the information we need in a very optimized way. So the next thing is the demo. So we have our demo guy switching over. So now this is the real application we have. This is the demo client. What you can see here is you have all the BeagleBones, German and Austrian. We have an aggregation layer, which is Germany and Austria. Now, looks like somebody has pressed. Yep, cool. So we recognize that. So it's 0 to 1 for for Austria. And you see now, can you move that away? Now it starts to blink. So what we see is the device does something, and you immediately see the reaction. So what you have to know is the Austrian traffic lights are 50 seconds behind because it's just programmed that way. If you have a German traffic light, I'm not sure, there should be one without the box around it. So just press the button there. It's immediately doing things. So German traffic lights are faster, but you see you have to run it a little bit to be safe. So that's what's happening. Yeah, 2 to 1. So cool. So go, go. So also on the right side we have the historian. I said before. Sadly, we have a little bit of screen resolution issues because of the recording. So it would go a little bit like over the edge here. So we have the chart for the last 60 seconds. Everything is stored on the server in the background. So we can have a look at yesterday and the day before. But yeah, actually that's it. So please now somebody press a lot of times, up to 10, 15, go ahead please. So, and now we see in a few seconds, yeah. Now we have a warning, we have the next warning. So this is what I said, the aggregation layer. We have, normally this would be split up in different screens. Now we see, okay, Germany, there is something wrong. I dig deeper into the data and I see the fault on the device or even on the value layer. So I have the hierarchy from up down here to the specific value. Now, and this is exactly what's important. If you have big systems, complex communication systems, you don't want to have all the windmills publish all the data to some broker to be sure that you gather all the values. No, what you want to do is you want to have a lower device, a thing which has the logic to work on its own, because if you just unplug one of these BeagleBones from the network, the traffic light will still work. Still, you see that the communication, so if you want to try, you can unplug it. The problem is the BeagleBones sometimes don't come up again when you replug it because yeah, the power fluctuates and then the processor stops. This has happened. So what we can, for example, see down here, if you scroll a little bit to the left again, we made, on the IT playground, we made a demonstration with BitReactive. They have some programming tool as well, publishing to MQTT. Now, if you press a button on their Raspberry Pi, we get a message and the count is going up. Okay, somebody unplugged it, or the battery failed, whatever. So we see now also the aggregation works the same way. We have the information, the device is offline, and we could also react to this if we would like to. So that's basically what we have here from the visualization of Eclipse SCADA. Of course, there's lots more in the background. Yeah, we show the latest events. Maybe you can open the detail dialog once again, and just disable one traffic light. So we have also, of course, the command options. Just to say disable, so the device reacts from some supervisory control, so it's not safety related. The traffic light would have the obligation to shut down in a secure manner, so that nobody gets hurt. And you also have down here the log. So what we did here is we just accept every command. That's okay. In a normal scenario, you would have some kind of security, some kind of cryptographic signature for each request that you can say, okay, this guy did that, and I can prove it using public key infrastructure, for example. Okay. I would like to hand over to my colleagues.
I don't have an operator, so. Okay, I don't have a demo guy, so I have to do it myself. No problem. It's really working. So what you see here is Phoniac, and this is the full application model of our traffic light. So it's in principle, the main components is the crossing controller, the car light controller, and the pedestrian light controller. You already see that I have been online. I'm currently not online, so it's not the real values of one of the traffic lights. And you can see here how they would connect and how to see the values here. For example, I've seen that 59 times the car light has changed its value during I was online. What you also see here is, for example, this is my interface to the I/O. This is a nomenclature for PLCs. So Q means output, X means a bit. So I have here three components for writing outputs. On the other side, you see the same here for input X, reading the pedestrian request, the button. And with publish blocks, I publish data. In this case, I publish only data to Eclipse SCADA, but I could use it also to communicate if crossings need to synchronize. I would use this as the same. If you look into such a traffic light, you can model the interface, you can model a state machine, what's going on. So it initializes with out of service, and then depending on what events and messages it gets, it will move through it. And I think I would shortly try going online. Let's see what's happening. Yeah, looks good. Just as a check, trigger event. Oh yeah, I'm online, that's working. So what you see what I did is I even did interact with the traffic light myself. It should be traffic light Austrian 5. So it's now blinking orange. You can press the button, but yeah, you see here pedestrian request, but nothing will happen because I'm not requesting anything. But you see also here the orange blinking, and you could say, okay, I don't want the orange light to turn on, so I force it to false, if I could type, and it will go to false. Even behind the logic would say change, the output will stay that way. This helps you when you're setting up such systems. Then you can say, okay, some parts of the system are not available, and you need to set things. If you want to see more of it, oh, sorry, wrong button. If you want to see more of it, we are downstairs, and
Thanks, Alois. Yes. Okay, so next thing we want to show is eTrice. So the German traffic lights are we use eTrice to develop. The modeling method is ROOM, real-time object-oriented modeling. It's a component-based modeling method. We have, in this case, for example, an application that has a timing service I double click, and here I have the component for my system. For example, in this case, the GPIO interface of the beagle bone hidden behind a port. The port is a formal specification, has a formal specification of this interface. In this case, message passing, bidirectional, asynchronous. And the traffic light controller here implements the behavior of the traffic light, so the state machine that does the application. And the third component I have in here is the Eclipse SCADA interface. So that's an aggregation of data. I dig in and I see that's the real protocol interface to Eclipse SCADA or to the SFP protocol. Just to show you an example, that's the structure of the program. So you can model really big embedded systems in a very nice manner because everything is encapsulated. Everything is very abstract and still formal enough to give you the power to generate the complete code. So I show you how the behavior is modeled. We have hierarchical state machines. You also can add manual code wherever you want, but the regular implementation for behavior is a state machine. Those are hierarchically. So first we go into blinking, and if I receive the activate command of Eclipse SCADA, I go to working. So in blinking, double click, I go to on and off, and if I activate the system, I go into working, and that's the actual behavior of the real traffic light. And if we press the button again in Eclipse SCADA, or if we deactivate it, it finishes its thing. So that's the safety part of this kind of system. You don't want somebody else to turn off the traffic light and people are dying or have to hurry a lot not to. So the traffic light finishes its process and then it goes to a safe state. So that's so you do not want to publish everything, especially not the commands. So in the end, you generate the code and you compile it, deploy it as any C program, and in the end, let me show you that. In the end, you can debug, for example, on model level, generate a message sequence chart and see exactly which component, which state is triggered by which message and so on. So that's a very powerful way of debugging distributed embedded systems. So just animating the state machine is not enough. So you need something to really dig in. Okay, so that's the eTRICE part, the second demo, and now we continue with the third demo.
So as we already just saw, these devices can get quite complex, and the complexity is sometimes just hidden in the thing. So at some point it's good to have an overview, of course, but at some other times you need to dig in deeper into the system. So for example, if you have a short look at some detail value here, we can go into the item list. So the item list, this is something, some user control we have here is what is behind that dialog box. So what's the pool of data we have, and you can also click more detail to see, okay, what's the state, what's the additional information. That's a lot of stuff. I don't go deeper into it. Now if you double click on here, you get even more structured information, but still this is all what you have in the UI, and at some point you want to go even deeper. So we have a tool, we have an app for that. So you can switch to that, please. So what we have here is, this is the admin client, is what we call it. So we have connections, so it's just a tool for us to do things, to look into it. So it looks like you have the wrong one. Just take the other one below. No, that one?
Doesn't matter. Just change the IP.
Okay. So we still have the old IP addresses for the Wi-Fi in there. Yeah, it's timed out because there is no Wi-Fi.
That should work.
So yeah, so now we see how we are connected. Now we're digging into the device. It's a very simple device in this case. You can take the values, you can inspect these. So you are debugging into the device. You can issue commands. Of course, this is all using the same protocol features. So you have also the same security that we normally have. You can trigger commands. You can, like you have seen from the outside, trigger stuff which is inside the box. However, we are bound to the interface, to the protocol that the box allows us to interact with. So as Alois just showed us, he can dig into the application, to the logic. We cannot do that. We can just take the commands that we are granted by the application inside the box. So I think that's a good last slide, please. So, of course, all of this, what we've seen is just the tip of the iceberg. There's lots more, and we have on the IoT playground downstairs. You can have a more detailed look from what you're interested in. So, any questions? Okay.
Thanks for your attention.
Yes.